Yesterday? Yeah, I was.
I think so.
Yeah, I think so. We were talking about Stieltjes functions and things like that, and the fact that in physics, we're very lucky that we're trying to solve physics problems because, there aren't any of the crazy things that might happen. Physics actually works extremely well, and that's because you're solving a Schrodinger equation, and the eigenvalues for a Schrodinger equation have very nice properties. Okay, so what we argued was that if you have some sort of differential equation like this, okay, you have some sort of Schrodinger equation like this, we argued that to solve this problem, the first step is putting in an epsilon. That's what we did on the very first day of the course. Okay, insert an epsilon. Now you're not solving one problem, but you're solving an infinite number of problems. And for each problem, there's a different eigenvalue. They all depend on epsilon. We assume a series in powers of epsilon. Okay. And to our shock, we find out that the series is a divergent series, so the equal sign is not right. So we have to replace this by an asymptotic sign, okay, as epsilon goes to 0. And now that we have a divergent series that represents the answer we're looking for, what do? And what we are very, very lucky to find out that, in fact, E of epsilon you can prove not from this, but directly from the problem that we're trying to solve, from the Schrodinger equation, that E of epsilon has all the properties that you want, namely properties 1, 2, 3, and 4, so has properties 1, 2, 3, and 4, and this implies that E of epsilon is a function of Stieltjes. And now we're in great shape. Because now that we know that it's a function of Stieltjes, this tells us that the pades converge. So what you can do is, you can take this series and convert this series, n equals 0 to infinity, a sub n epsilon to the n. You can convert this series to a sequence of pades. And there are two sequences you can have. You can have the sequence Pnn of epsilon, and you can have the sequence Pnn plus 1 of epsilon. Okay? And now that you know that it is a function of Stieltjes, each of these separate sequences converges. Okay? This guy converges downward, this guy converges upward. So as a function of n, if you draw the sequences, this sequence here looks like this. The lower sequence looks like this. And what we know is that the correct answer, and of course, all the terms in this sequence lie above all of the elements of that sequence. Okay? So you have two monotone sequences bounding each other, and a bounded monotone sequence converges to a limit. Okay? That's one of the early theorems that you prove in first-year calculus. So we know that this sequence approaches a limit, that sequence approaches a limit, and it would be really great if they approach the same limit. Okay? In fact, we know that the answer that we are looking for, E of epsilon, is is greater than all of the elements in that sequence, p n plus 1, okay? And it's less than all of the elements in that sequence, for all of it, okay? Yeah?
What happens if we do Shanks on this right now? Do we get closer to the answer?
If we do a Shanks on this,
Yeah.
That's a very interesting question. If this sequence, if this is converging to the same limit, then it will converge very, much more rapidly to that limit, so that you can extract many more decimal places. Okay, so what we have been doing is only taking the raw limit. We haven't tried to accelerate the limit. However, if they do not approach the same limit, that's a very interesting question, because the Shanks may not converge to a limit. It may converge to two limits. Okay? There's no reason why the Shanks has to converge to one limit, and it can converge to two limits. Okay? Furthermore, if it converges to one limit, there's no, I don't know, I mean, there may be two possible outcomes. Okay? If it converges to one limit, there's no guarantee that that limit has anything to do with the correct answer. Okay? So there's some danger in doing that. Okay? But that's a very interesting question, and it would be very interesting to see what happens. I don't know if I ever tried in the case of an x to the 8 potential. We're going to talk about that in a second, but in that case, don't know whether or not the Shanks converges to two limits or to one limit. I'm not sure. I'm not sure what happens. But it may just be converged to something noisy. You see, because when you go very far out, this is essentially horizontal. And this is essentially horizontal. So when you calculate the Shanks, you get nonsense. I mean, this number and this number are effectively the same number. But the middle number is different. So you compute the Shanks from three subsequent things, right? So you either take two of these and one of these, or you take two of these and one of these. So you're going, bloom, 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 like that. Three successive things. If you do that, almost certainly you're going to get two limits. Okay? Simply because these two numbers are, for all intents and purposes, the same. So that's an interesting question. But it would be worth trying to see what happens. And you can generate those numbers quite easily for an x to the 8 theory. It would be a nice project to see what happens. The reason is that you can get as many terms in, as many coefficients as you like, just by solving a simple recursion equation. Okay, you don't have to use Feynman diagrams or something hard to calculate these numbers. You can do it using the recursion relation. If you're interested, I'll show you after class. And it's published. In fact, you can read it. There are lots of papers. Okay, so the problem is whether or not this limit and that limit happen to be the same limits. Now we do know, because it's a function of Stieltjes, that this is true. But we still, so at least we know roughly what the answer is going to be. You understand, if you do this problem numerically, if you actually sit down in front of a computer and do all this junk, these two numbers will be very close together. I mean, this number might be, 3.25, and this might be 3.35. So there might be only a very small distance between those two numbers. So if you're happy with 1 or 2 decimal places, 1.5 decimal places accuracy, you can say the answer's in there and I'm happy. You can walk away. But that's usually not very satisfying. So we would like to know more. And this is what I started to talk about last time. So this has to do with the Kármán condition. And the Kármán condition says that if a sub n grow no faster than, if this bunch of numbers, a sub n, grow no faster than 2n factorial, then L1 is equal to L2 and everything is great. Okay? And interestingly, if v in that, so if v of x is just, say, x squared, and w of x is x to the fourth, then a sub n grows like n factorial times a constant to the n. So it's the n factorial that's important. And the question is, why does it grow like n factorial? And in fact, so you've studied quantum field theory, you've had a little bit of experience with phi to the 4 quantum field theories, right? You've done a little bit. Have you done any renormalization?
Yeah.
A few graphs, things like that. Good. Okay. So this is in fact behaving just like a phi to the 4 quantum field theory. So in fact, let's try to understand why this is growing like n factorial. So I'm going to give you a heuristic argument. Okay, I'm going to make lots of jumps, but the argument can be made quite precise. Okay? So roughly speaking, why is there an n factorial? Well, that's easy to explain. If you have a g phi to the 4 theory, and you're trying to make some sort of perturbation calculation, so you're calculating a Green's function of some sort, it doesn't really matter what kind of Green's function you're calculating. You start drawing Feynman diagrams. And a Feynman diagram is nothing but a bunch of dots called vertices. And coming out of each dot, there are 4 lines. Why are there 4 lines? Because it's a phi to the 4 field theory. Okay? So what are you instructed to do? You're instructed to connect up the lines, okay, and add up all the graphs having n vertices. Okay? So if you sum up all graphs with n vertices, the sum of all those graphs. Now, when I say the sum of the graphs, a graph is just a bunch of dots and lines, but Mr. Feynman, very interesting character, by the way. Any of you read some of his books? Yeah? My uncle was Feynman's high school teacher. He talks about his high school teacher, how much he loved his high school teacher, and how his high school teacher got him interested in physics and gave him a book on variational calculations and things like that. That was my uncle. Very nice character, by the way. I spent a summer with him when I worked at Caltech for a summer just for fun and did some research. Feynman was there, so we used to have lunch every day, a bunch of us. Quite an interesting guy to work with. Fastest thinker I've ever met. No one else I've ever met has come even faintly close. We'd sit at lunch and he would say, in his Brooklyn accent, I also have a Brooklyn accent, but I conceal mine, and he worked on his. He practiced in front of the mirror. He would say, so how's it going? And we'd say, there were 3 of us who were working on calculation. We'd say, well, we showed this and this and this and this. And we'd say, very good. Bullshit. He always said that. And the first time he said it, I was stunned. And he said, you see, you showed this and this, but that implies that. This implies this, and that follows from that, and therefore you're wrong. Contradiction. And we could never answer him. And we'd go off and we'd calculate all afternoon and all next morning. And much more often than not, he was wrong. But we couldn't, on the spot, show why he was wrong. You had to really go deeply into the problem. But when we finally understood it, we went back the next day. We'd sit down at lunch and he'd say, so how's it going? We'd say, well, you said yesterday that, but in fact, there's a contradiction in your argument because you assumed that this was true, but that's not. He would say, very good. You never took it personally. Perfectly happy to just think about science without getting personally involved. And then he would say, yes, very good, very good. Bullshit. And then he'd come up with something else. And this would go on and on and on. It was very interesting. Very interesting. By the end of the summer, we had a good project. So Mr. Feynman explains to us how to turn this bunch of dots and lines into a number by evaluating some intervals. Okay? You add up these numbers, so when you sum up all the graphs, I mean you sum up all the numbers associated with those graphs, having n vertices, and that is equal to the nth term in the perturbation expansion. So the question is, how big is that? Okay? So let's imagine that you have n vertices. Okay? And each vertex has 4 lines coming out of it like this. Okay? Now, if you were to try to construct all the graphs, of course, there might be some external lines. You might have some external lines coming out, but there's only a finite number of them. So who cares? We don't care. It doesn't make any difference. So for example, if you're calculating the 4-point function, there would be 4 of these lines connected to the outside world, but that's only 4. Who cares? Okay? So the rest of the lines, the rest of these dots are connected to themselves. So how many graphs are there? Well, let's pick any line at random, say that one. How many possible places can we connect this line to?
4n minus 1.
4n minus 1, okay? So there are 4n minus 1 loose ends sticking out, so we just connect it to one of those lines. Okay? So there are 4n minus 1 ways of doing that. There are, of course, 3 more lines coming out of here, and so on. Okay, now we pick another line at random. Who cares which one? Say this one. Okay? How many possible ways are there to connect this line to these graphs?
4n minus 3.
4n minus 3. And we continue this process, okay, until everything is all connected up. So we continue like that. So that gives us 4n minus 1 double factorial. You all know the symbol double factorial, okay? It means you're multiplying every other number together, just the odd numbers, 4n minus 1, 4n minus 3, 4n minus 5, and so on. Okay. However, we are overcounting. Why are we overcounting? Okay. Well, to begin with, these vertices, we've assumed that they're all identical. Okay, we've treated them identically, but we have to divide out all the possible rearrangements of those vertices. Okay, if we label these vertices 1, 2, 3, 4, 5, there are n factorial labelings for those vertices. So we have far too many graphs, so we have to divide by n factorial. Okay? We still are overcounting, okay? Because when I said we take this line and connect it to this, okay, we could just as easily have connected it to this. You see? Or to this. Or to this. Okay? So when I connect it to a vertex, so these lines coming out of the vertex are identical, and when I pick those lines or connect to those lines, there's a rearrangement. I could have gone to this line first, or that line first, or that line first, or that line first. So I'm going to number these, 1, 2, 3, 4, in that order. That means there are 4 factorial arrangements of those lines. So I have to divide by 24. Okay, 4 factorial. But wait a minute, there are n vertices. So I have to divide by 24 to the n. Okay? That's how many graphs there are. Now I know what you're thinking. You're thinking, wait a minute. It could be that the graphs that you drew, that when you drew these graphs, it could be that this was connected to this was connected to this was connected to this. It might have come out that this was a disconnected part. And the kinds of graphs that we are interested in quantum field theory are connected graphs. Okay? However, in the counting of graphs, the chance of this happening is so slim that we don't care. It turns out it doesn't make any difference in the overall count in the number of graphs, asymptotically. Okay? All it does is it changes the overall constant out front. Okay? There may be a factor of 1/2 or 1/10 or something like that. But in terms of the growth of the number of graphs, we don't care. We just don't care. Great. So how big is this when n is large? Well, let me turn this into a factorial.
A question.
Yeah.
What are you basing this fact on, that you have not that many disconnected gaps?
Oh,
Yeah.
I've done the calculation with great precision. Okay, and I can cite a paper for you. So I'm going quickly.
But my
So I'm not going to give you the argument, but I can, after class, if you like, I can go into detail about it. But it turns out that the number of connected graphs compared with the number of graphs, that the difference is irrelevant. Okay, in fact, asymptotically, the number of all graphs compared with the number of disconnected graphs, if you take that ratio and let n go to infinity, it approaches 1. Okay? And I'll show you why that is. It has to do with the fact that that you can write down the generating function for the number of graphs, and you can write down the generating function for the number of connected graphs. Okay, so if a sub n is the exact number of all graphs having n vertices, and Cn is the number of connected graphs. So Cn, of course, is smaller than An. The number of connected graphs is smaller than the number of all graphs. Okay, right? And if you write down the generating function, a sub n x to the n, call that f of x, okay? And c sub n x to the n, call that g of x. So this is the generating function. Then the relation between f and g is very interesting, okay? Turns out that the sum of all graphs, okay, is the exponential, right, 1 plus the sum of all graphs, is the exponential of the number of connected graphs. Okay, this is a precise statement relating the number of all graphs here to the number of connected graphs here. Very interesting. And from this you can derive a difference equation satisfied by a sub n and c sub n. Okay, and it's something like a n minus c n is the sum from j equals 1 to n minus 1 of a n c, or aj c n minus j, something like that. And from this, you can solve this equation asymptotically. This is convolution here. Solve this equation asymptotically and show that a sub n is asymptotic to c sub n as n goes to infinity. So, okay, so I can go over details with you. Okay, question is, how big is this? Okay, and let's make this into a factorial. And the way we can do that is we can just turn this into 4n factorial if we multiply by all the numbers that are missing. Remember, all the even numbers are missing here. How many numbers are missing? Well, we would have to put in the denominator, we would have to put in 2n factorial times 2 to the 2n. Okay? Okay? So there are 2n numbers that are missing from here. So what are the two numbers? They're all the even numbers between 2 and 4n. Okay? And those numbers are 2n factorial times 2 to the 2n. All right, good. So how big is this? Well, we can calculate how big that is. 4n factorial is roughly 4n to the 4n times e to the minus 4n. That's the Stirling formula, right? And n factorial is roughly n to the n e to the minus n. 24 to the n, well, that's just 24 to the n. And 2 to the 2n, well, that's just 4 to the n. Okay? And 2n factorial is 2n to the 2n times e to the minus 2n. Did you see all that? Is that clear? So each of those factorials can be approximated by this and this and this. Okay? So this is an approximation to these factorials. But now we can simplify this. Let's see what we've got. We've got an n to the n here, n to the n, and n to the 4n, n to the 4n here. And here we have an n to the 2n. Okay? Then we have numbers. So here is a 4 to the 4n, and we have that number. We have a 24 to the n from here. We have a 4 to the n from here. We have a 2 to the 2n, which is another 4 to the n. 4 to the n from here. Okay, so those are various numbers to the power n. And then we have exponentials, right? We have on top e to the minus 4n. And on the bottom, we have e to the minus n and e to the minus 2n. Here's the e to the minus 2n, e to the minus n, e to the minus 4n. So I think that's everything. So now let's simplify this. So altogether, we have n to the n, n to the 2n, n to the 4n. So we have overall n to the n. But what about the e's, the powers of e? E to the minus 4n, e to the minus 1n and 2n, that gives me e to the minus n. Okay? So that takes care of these numbers. Then here we have 4 to the 4n, right? So that gives me altogether 4 to the n, 4 to the n, 4 to the n, and 4 to the n. 4 of them altogether. This cancels 2 of them. Got it? So we now have 16 to the n over 24 to the n. Okay? So 16 to the n over 24 to the n. We don't really care about this. This is just some constant to the n. And this is approximately n factorial. So the number of graphs is roughly n factorial times some constant to the n. This constant is 16/24, but who cares? Doesn't make any difference. So the number of graphs is growing like n factorial. That's a good thing. Because with that estimate, we now know that we have satisfied the Karl limit condition, and that's why you can do this calculation. It just works from start to end. We know that the PADEs are going to converge, and they're not only going to converge, they're going to converge to the right answer. Isn't that a fantastic? This is a real tour de force. Okay? We start out with an infinitely hard problem. We break it down to an infinite sequence of solvable problems. We get a divergent series, and we sum the series. And with the theorems of Stieltjes behind us, we know that when we sum that series using PADE, we're going to get the right answer. This is really fantastic. Okay? Yeah.
Is there a connection with renormalization?
No. In fact, here I never said anything about renormalization. But the counting of graphs doesn't change when you renormalize, because you're just subtracting graphs from one another. So that doesn't make any difference. When you renormalize, what happens is that, in higher dimension, not here, because in the work that we've done in quantum mechanics, you don't get any infinities. But in higher dimension, some of these graphical integrals, not all of them, but some of them diverge. So you need to do subtractions. Okay? But it doesn't change the fact that you have a growth like n factorial times a constant to the n. It still gives you, after renormalization, the series still diverges. It still has the zero radius of convergence. Okay? And it's Borel summable, or PADE summable. So if you repeat this argument, however, for a phi to the sixth theory, you can sort of see what's going to happen. If instead of a phi to the fourth theory, if we did a phi to the sixth theory, then there would be two more lines coming out of all of these vertices. Okay? And if there are two more lines, then instead of 4n minus 1 factorial, what would you have? 6n minus 1. So now, when you do this calculation, instead of ending up with n factorial here, you'd end up with 2n factorial. And if you had a phi to the eighth, instead of 6n minus 1 factorial, you'd have 8n minus 1 factorial. And so this would be 3n factorial. Now you violated the Karl limit condition. So you have a problem. Okay? It's very interesting. Very interesting problem. Of course, I just gave you a heuristic argument. Part of what you have to show is that, I didn't say what happens when you do these integrals. You might think, wait a minute, maybe some of the Feynman integrals give you a small number, like 1 over n factorial or something like that. Is that possible? And the answer is yes, but only an insignificant number of Feynman integrals can give you something very, very small that might compensate for n factorial. The average Feynman integral goes like a constant to the n. In fact, what you can do, and this is really wonderful, this is really fun, you can study the statistical behavior of Feynman diagrams. Okay? That is to say, you can imagine, instead of, when you do statistics, you start out by thinking of, the simple model is you have a box with gas molecules in the box, and you can study the thermodynamic properties of gas molecules, many of them, in a box, and talk about entropy, and talk about a distribution, and talk about temperature, and so on. Okay? Well, here you have a bunch of vertices. You can have a huge number of vertices. You can let n go to infinity. And now, what does a Feynman diagram look like? It looks like a pot of spaghetti. Okay? An incredibly complicated mass of lines. Infinite numbers of vertices and infinite numbers of lines. And you can study the distribution of graphs. Okay? And you can actually come up with the concept of an average graph, just the way temperature is an average measure of gas molecules in a box, okay? And pressure is an average measure of molecules in a box bouncing around inside of the box. Okay, so there are various thermodynamic quantities. The same is true with Feynman diagrams. Okay? So as n goes to infinity, the Feynman diagram becomes a continuous, it's not a bunch of individual dots connected by lines like this, okay? But it's a continuous bunch of dots connected by a continuum of lines. And you can study those thermodynamic properties. You can go to the limit of continuous Feynman diagrams. Not discrete graphs lines connected by dots, but sort of a sheet of dots and lines, okay? And if you're interested, I can recommend papers and things for you to read. Very interesting stuff. I think I should say one more thing before we could move on, and that is, you know, these are rough estimates that we made. We estimated that the reason that perturbation theory diverges is that there are a lot of graphs. Okay? That's all. That's why perturbation theory must be divergent. Okay? But can you come up with a much more precise statement of how rapidly perturbation theory diverges? And I want to give you an indication about how you can study, you know, this is imprecise, but suppose we wanted to know precisely a sub n is asymptotic to what as n goes to infinity? Can you give me a precise answer to that question? How would you go about doing it? And there are a number of ways of going about doing it. You can do the statistical mechanics of Feynman diagrams with great precision. And there are lots and lots of research projects there for you to do. Okay, so I've written a number of papers on the subject, but this is basically an untrodden area, very interesting area. But let me give you one very interesting way of answering the question. Because this is a fairly elementary way of approaching the problem. So, how would you go about doing it? We're imagining that you have, just to make things simple, we're imagining just that Schrodinger equation up there, and we are calculating this function. E of epsilon is asymptotic to the sum of a sub n epsilon to the n. Okay? Now, for the problem that you were looking at, just think about it a second, to be a little bit more precise, if we had the Schrodinger equation where we had an x squared over 4 plus epsilon x to the 4th over 4, you did, isn't that right, Tibor? You spent some time in the tutorials, and you found that the perturbation series begins, for the ground state energy, begins 1/2 plus 3/4 epsilon minus 21/8 epsilon squared plus 333 over 16 epsilon cubed. You saw that, and you should be a little bit upset by this, because this is obviously not a Stieltjes series. Why is that? Here, all along, I've been saying that you can use pod A, but there's a little bit of imprecision. Yeah?
The first term is the wrong sign.
That's right. It's not alternating in sign. The Stieltjes series, the first property, the most obvious glaring property of the Stieltjes series is that it's an alternating series. So you're completely correct. But it turns out that to correct that problem is very easy. You simply subtract 1/2 and divide by epsilon. Okay? So it's not really E that I'm interested in, but rather E minus 1/2 divided by epsilon. okay? Because this is asymptotic to 3/4 minus 21/8 epsilon plus 333 over 16 epsilon squared, and so on. And it's this that is a Stieltjes series. Okay? So to be precise, this is the thing that is a function of Stieltjes. And this is the thing that is Herglotz and so on. Okay? All right. And this is the thing that is analytic in the cut plane. And that's the key point. Analytic in the cut plane. Aha. Here is the cut. Here is a cut plane. Here is the point epsilon right there, say. There's epsilon. We'll call this the t-plane. What does the Cauchy theorem say? This is starting out just like what I was saying last time. What does Cauchy's theorem say? It says that E of epsilon can be written as the integral around some contour like this of dt over t minus epsilon E of t. Okay? And just as we did last time, we can push this contour around like that. Okay? Let this go off to infinity. And so you can show that E of t can be written as an integral from minus infinity to 0, and there's a 1 over 2 pi I here. 1 over 2 pi I times dt over t minus epsilon. And instead of t, what we have is the discontinuity across the cut. Okay, and the discontinuity across the cut is 2 times the imaginary part of the energy. The discontinuity. Okay, 2 times the imaginary part of the energy times I. Okay, and let's cancel a factor of 2I. Now I'm going to do something very strange. I'm going to say, wait a minute. In this integral, I have 1 over t minus epsilon. Okay? Just for laughs. Okay? Just for laughs, I'll write that as 1 over t times 1 over 1 minus epsilon over t. And I will write that as the sum from epsilon from 0 to infinity, epsilon to the n over t to the n. Okay? And I'll stick this right in here, and I'll integrate term by term. Now, if I do that, that means I'm illegally interchanging the orders of integration and summation. But I'm going to do it anyway. Of course, I know that because I'm doing it illegally, I'm going to wind up with a divergent series. Which divergent series? You know perfectly well which divergent series. It is the divergent series for E, which is a sub n epsilon to the n. Okay? Of course, I have to be careful. This is not really an equal sign, but it's an asymptotic sign. But asymptotic series are unique, and therefore, I can identify the nth term here with the nth term here. Got it? So I conclude that the nth term, a sub n, can be written as an integral from minus infinity to 0 dt over t to the n plus 1, t to the n plus 1, okay, n of these and n more, and 1 more, times the imaginary part of E. This is an equality. What I showed you was that the nth term in the perturbation series is the nth inverse moment, not a moment, this is a strange kind of moment, it's the inverse moment of the imaginary part of E for negative t. Woo! Okay, so now let's be very careful.
Shouldn't you have 1 over pi?
Yeah, and there's a 1 over pi. That's right. But this is an exact statement. Okay? Now this is incredible. Okay? Because we have a formula for the nth term in the perturbation series. Now, let's think about what this formula means. This is a really interesting formula. We wanted the nth term in the perturbation series for the potential. So we started out with the potential x squared over 4 plus epsilon x to the 4th over 4. And we wanted a sub n. That is the coefficient in the perturbation series, you know, a sub n epsilon to the n. And we've come up with the conclusion that a sub n is the nth inverse moment of the imaginary part of the energy. So there's a t to the n, dt, n plus 1, n plus first, inverse moment. Okay? But we are calculating E for this value of t. T is real, but negative, right? You see this? It goes from minus infinity to 0. That means, so this is what we're instructed to do. Take the imaginary part of the energy when t is negative and integrate it. So we're not calculating in this potential because we always were assuming that epsilon is positive. In fact, what this calculation instructs us to do is to consider the potential x squared over 4 minus t times x to the 4 over 4. Or it's plus t, but t is negative. T is a negative number here. You see that? You all see that? This integral goes from minus infinity to 0. So I'm to calculate the imaginary part of E. What is the imaginary part of the energy? And what does this potential look like when t is negative? This potential looks like this for epsilon positive. But this potential looks like this because t is negative. So if we're calculating, say, the ground, there are a bunch of energy levels here. If we're calculating the ground state energy, we have to go down here and stick this ground state energy in this well. What happens if you put a particle in this well? It escapes. Why is that? Say again? It's tunneling, right? This is tunneling. So it tunnels through the barrier and escapes off to infinity. So the state now decays in time. It's radioactive. It has a half-life. What is the imaginary part of the energy? It's the decay rate, right? It has to do with the lifetime of the state. Do you see that? So I've shown you that the nth term in perturbation theory corresponds to taking the nth inverse moment of the lifetime of a state in an upside-down potential. Woo! And this came out of an analytic continuation theory. That's what we did by pushing this contour. In fact, what we derived is called the dispersion relation. How many of you have heard of a dispersion relation? Okay, a dispersion relation comes from doing an analytic continuation. And the dispersion relation relates two quantities that are not at all obviously connected. We are relating the large order behavior of perturbation theory in this potential to the lifetime of a state in this potential. wow, they're not at all obviously connected, but this is not just an approximate statement. This is an equality. This is an exact statement. And now I can use WKB theory, oops, that's something I'll be teaching you starting now, to calculate the lifetime of a state in this well. And if I take that lifetime from WKB and substitute it into this integral, I can then give you the asymptotic behavior of A sub n for large n. Okay? And that gives you a precise statement. And what you learn from this calculation is that A sub n is a precise asymptotic behavior is minus 1 to the n plus 1 times n factorial, okay, and more precisely gamma of n plus 1/2 times 3 to the n times the square root of 6 over pi to the 3/10. And that's the precise asymptotic behavior as n goes to infinity. Okay. So we had, over here, we gave a rough argument. We said it went roughly like n factorial times a constant to the n. But this is the precise asymptotic behavior. Okay. Yeah. I'm not going to talk any more about that because this gets very, very
So I missed a connection there. You said that it's not E, but E minus half by epsilon, which is analytic on the cut plane.
yes.
But then you
To
did,
be precise, instead of substituting E in here,
oh, so you
this
would
is
use that
imprecise.
whole,
You
whole
really
expression.
need
I see.
to substitute that to
Right.
do a more careful calculation. You really have to do that. Okay, and I'm not going to go into the details of that. The reason is that this is not, there's a problem with this function at infinity. And with this function at infinity, when I go off to infinity, I actually do get a contribution from this outside loop. But this gives me an extra factor of 1 over epsilon. And now I no longer have that. So it's really, to do this very, very precisely, instead of using E, I really have to use this. Okay, but I'm not going to go into the details of that. Okay? Okay, I think you now have a picture, but now, to complete this course, I want to talk to you about WKB, because this is a fantastically beautiful way of solving problems. I think I have, enough time to give you an introduction. So, okay, good. So unless there are any questions, that sort of completes what I wanted to say about an introduction to perturbation theory. And WKB is an example of a very, very powerful kind of perturbation theory. It is called, let me give you the history of it just quickly. What does WK and B stand for? What does it stand for? That's right. W is Wenzel. Okay. Do you know what the question is whose answer is 9W? Can you think of a question whose answer is 9W? The question would be, tell me, Mr. Wenzel, do you spell your name with a V? You would say 9W. All right, never mind. So W is Wenzel, K is Kramers, B is Briand, and this method that I'm going to tell you about is named after these guys, and it's completely unfair. And people who work on this know that this is not an appropriate name for what I'm going to teach you, but it's stuck. So it's tradition. There it is. It's not appropriate because there's one guy named Jeffreys, Lord Jeffreys, who understood WKB far better and understood it before these guys understood it. And so if you read some books on WKB, they call it WKB J theory. Okay? However, Lord Jeffreys, even though he understood it a lot better than I never met Lord Jeffreys. That was before my time. But I met his wife, who was also a brilliant mathematician, Bertha Jeffreys. I met her, she was about 92. Something like that, when I met her, and very sharp. And we were sitting in a seminar together, and she was sitting in the front row listening to every word. And in the middle of the seminar, she stopped the speaker and she said, "Young man, you don't know what you're talking about." She was completely right. You should call it WKBJ theory, except that this is not historically appropriate because Lord Rayleigh understood it far better than any of these guys, and it should really be called R theory. However, Lord Rayleigh was preceded by Mr. Green. So maybe it should be called G theory, and nobody can come to a satisfactory conclusion about what you call this. So I'm just going to call it, I'm going to follow the inappropriate name, which is WKB. So that's the historical background. WKB theory goes under what field theorists call it is semi-classical methods, okay? But WKB is an easier word. It's easier to say WKB than it is to say semi-classical, okay? For me, anyway. And where does WKB come about? Well, we're solving the Schrodinger equation, which is, minus y prime plus v of x y is equal to e y, okay? And typically what we do is we say, fine, we'll put y double prime on the other side of the equation. This is equal to v of x minus e times y. So in general, we're solving an equation of this form, okay? However, as you know, this is the dimensionless Schrodinger equation. And there is something that goes in here, which is h bar squared, some nonsense like that. And people like to think, at least some people say, well, h bar is a small number. Okay, and so there's a small parameter in here. Okay, that's nonsense, of course, because h bar has dimensions. You can't think of a dimensional number as being small. So that's not appropriate. Okay? But what we're going to do is we're going to say, if h bar goes to 0, then the theory in some sense becomes classical. So the difference between classical physics and quantum physics is something like taking the limit as h bar goes to 0. So if we're going to do a semi-classical, that means slightly quantum calculation, we should imagine putting a very small number here, and it's traditional to insert a very small number squared for reasons that you're going to see. Okay, so we could put an epsilon over here, but it's an epsilon squared. Now, right away, you can see that this is a very strange kind of perturbation theory. Why is that? Why is this a very strange way of putting an epsilon to the problem?
Because epsilon equals 0, you don't have
Right,
equation. Yes.
right. That's exactly right. So if epsilon is non-zero, this is a differential equation, second-order differential equation, and the solution contains two arbitrary constants so that we could satisfy two initial conditions or two boundary conditions, right? And if you set epsilon to 0, this becomes an algebraic equation. In fact, a trivial algebraic equation. And we're going to do it anyway. Okay? And that's why WKB is so interesting. Okay? So the question is, what does the perturbation series look like? It can't possibly look like a Taylor series. It can't possibly look like a Taylor series. This could not possibly be right. It couldn't be that y looks like y sub n epsilon to the n. This is not possible. Why is that? Why is that not possible? The reason is that, what about dominant balance? In the limit as epsilon goes to 0, if y has this structure, then the left side of this equation would be proportional to epsilon squared, and the right side would be proportional to 1. That's not a dominant balance. Can't possibly work. So it must be that y double prime is very big. It must be that y double prime is of order 1 over epsilon squared. Otherwise, how could you have a dominant balance between the left side of the equation and the right side of the equation? Okay? So let me show you the form of the perturbation series. It's very interesting. This is not the form of the perturbation series, but rather the perturbation series has the form e to the s, where s, so we're going to make the substitution y as e to the s, where s has the form 1 over epsilon times s naught plus s1 plus epsilon s2 plus epsilon squared s3 and so on. That is, it has the form 1 over epsilon times the sum of s and epsilon to the n. Okay? And the key thing here is that there's a 1 over epsilon out front. That's the idea. Okay? Now, so what we're going to assume is that y is represented by a perturbation series of the form sum of 1 over epsilon n equals 0 to infinity s sub n epsilon to the n. That's the assumption that you make when you do WKB. Okay, and this is called the WKB series. Yeah.
Can we put the equality before exponent?
Why can we? We're going to assume that the perturbation series has this form. We have to show that this is valid. Okay, so I begin my analysis by assuming that this is the structure of the answer. Okay, I'm going to try this series. I'm going to try finding a series of this form. And I'm going to show you that it's valid. That is, I'm going to show you that S2, I'm going to show you that S2 is negligible compared with 1. We don't see that yet, but we have to show that. Okay? Now, that is the S2 term, that is S2 epsilon, is negligible compared with 1 as epsilon goes to 0. We have to show that that is valid. It may not be true. Maybe that S2 is very big. So even though it's multiplied by epsilon, this may not be correct, but it is going to be correct. We're going to see that. Okay, and we're going to show that epsilon squared S3 is negligible compared with epsilon S2 and so on. Okay, as epsilon goes to 0. Okay, so what happens if we try? So this is the beginning of WKB. What we're going to say, let's experiment and let's see whether or not this is a valid way to represent y. Could that be consistent with putting an epsilon squared in the differential equation? So we're beginning with the differential equation epsilon squared y prime prime equals qy. So on the right-hand side, we get, if we substitute this perturbation series, we get e to the 1 over epsilon sum of s sub n epsilon to the n over here. And on the left side, we have y double prime. Okay. Now, when you calculate one derivative of this, you pull down this series multiplied by epsilon. You get the derivative. When you take two derivatives, you have either a 1 over epsilon sum from 0 to infinity epsilon to the n s sub n double prime, or else you have 1 over epsilon squared times the sum of epsilon to the n s sub n prime squared. Do you all see that? So this is the S double prime that we have looked at before. This is the S prime squared, and what I talked about last week. Okay, and this is the right-hand side of the equation. And all this is multiplied by e to the 1 over epsilon, epsilon to the n s sub n. And we can divide this out of both sides of the equation. And we conclude that epsilon squared, 1 over epsilon sum, epsilon to the n, s sub n prime prime, plus 1 over epsilon squared, sum epsilon to the n, s n prime, squared is equal to q. Is this possible? I mean, can we now have a dominant balance? Yes, we can. We now get a dominant balance. So let me write this out now very carefully. Okay? If you multiply epsilon squared times the first term here, you get epsilon times the sum from n equals 0 to infinity, epsilon to the n, s sub n prime prime. And over here, the epsilon squares cancel, and you have a square of a series. Do you know how to square a series? What is the nth term in the square of a series?
Sum over from 0 to n for the binomial coefficient on n.
Well, no, not a binomial coefficient. We're just squaring this series. Just squaring a series. So it's you end up with a convolution. What do you get when you square this series? The epsilons cancel. You have a series from n equals 0 to infinity, epsilon to the n. But the nth term in that series is a convolution. It is the sum from j equals 0 to n of sj, sn minus j. Do you see that?
So
And
you
this
have
is equal to q.
epsilon to 2n then.
No, epsilon to the n. Think about it. If you have a series a plus a0 plus epsilon a1 plus epsilon squared a2 and so on, and you square it, the first term of the series is a0 squared. The next term of the series is epsilon times a0 a1 plus a1 a0. The next term is epsilon squared times a0 a2 plus a1 a1 plus a2 a0, and so on. One term, two terms, three terms, four terms. It's precisely this. Okay? And now, one last step. You see there's an epsilon times epsilon to the n? Let me write that as epsilon to the n plus 1. And let's shift so that this becomes a series in powers of epsilon, so it becomes the sum from n equals 1 to infinity, epsilon to the n, sn minus 1 prime prime. Now, this is the starting point of WKB. And now I'm going to show you something absolutely wonderful. I mean, really wonderful. What is the coefficient of epsilon to the 0? Epsilon to the 0 in this system of equations. What's the coefficient of epsilon to the 0?
S0 squared.
Okay, S0 prime squared equals Q. Very good. We've seen that equation before, haven't we? Okay, this is a repeat of what we've done. You've already seen WKB. What you see here, solution to this equation, is S0 is equal to plus or minus the square root of Q integrated. Okay? Good. What's the coefficient of epsilon to the 1? Well, as soon as the power of epsilon gets higher than 0, I think we better raise this. Okay, as soon as the coefficient, as soon as the power of epsilon gets greater than 0, there's nothing on the right-hand side. So the first equation, so the coefficient of epsilon to the 1 here is just S0 prime prime. And the coefficient of epsilon to the 1 over here is 2 S0 S1 prime prime. What's the coefficient of epsilon squared? It would be S1 prime prime plus S0 prime S2 prime plus S1 prime squared plus S2 prime S0 prime, two of these, is equal to 0. And so on. Okay? And the coefficient of epsilon to the n, it is Sn minus 1 double prime plus the sum from j equals 0 to n, Sj Sn minus j prime is equal to 0. Now I want you to just look at these equations before we quit today. You notice that I have a trivial equation to solve for S0. There it is. Next, I want to solve for S1. But it's trivial, right? I just divide by this piece, put it in the denominator here, and that tells me S1. If I want S2, you notice S2 appears only linearly. It's right here. So I divide by whatever is multiplying it. I already know S1 and S0. So I can immediately say what S2 prime is, and then I take off the prime and integrate it, and I'm done. And in general, here's the nth equation. I can immediately solve for Sn prime is equal to blah, 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 okay, divided by something or other, and integrate it. That gives you Sn. This is amazing. Why is this so amazing? Because we started out with a differential equation that nobody knows how to solve. And we've reduced it to a sequence, an infinite sequence, of absolutely trivial equations. These are just trivial algebraic equations, and I never have to solve a differential equation. All I do is integrate this once, and integrate this once to find S1, integrate it once to find S2, integrate it once to find S3, 4, 5, 6. WKB is really, really wonderful. Okay? So I've reduced a differential equation to nothing more than introductory calculus. All you have to do is this integral, that integral, that integral, the next one, the next one. So I've reduced the problem of solving a differential equation to the problem of taking an integral and another integral and another. Just find S0, S1, S2. Do you see that? That's all there is to WKB, you might think. That's the base. That's the backbone of WKB. That's the idea. This is what comes from Mr. Green. Why is this interesting? Well, to begin with, it's not a conventional perturbation series. We are not doing conventional perturbation theory because the perturbation series is in the exponent. We're assuming that y is an exponential of a perturbation series. It's not a perturbation series. It's an exponential of a perturbation series. That's very interesting. That's the first thing that's very interesting. Second thing is, now I know you're going to be amazed when I tell you this, but this series is a divergent series. So in fact, you can't write an equal sign here. You can only write an asymptotic sign. And all of these calculations are assuming that asymptotics is valid, which it is, unless something goes wrong. And every once in a while, with WKB, something interesting happens. Do any of you know what is the, before we quit, can any of you tell me what is the interesting thing that might happen? That might happen, might not happen. What could possibly go wrong with WKB? Anybody know?
Some S prime equals 0.
If S prime equals 0, no, we don't care. 0, that's not. You notice here we calculated S naught. The next equation tells me S1 prime. And from this equation, we learned that S1 prime, here's S1 prime right here, it's equal to minus 1/2 S naught prime prime over S naught prime. That's what this equation says, right? But we just said that S naught prime, this is minus 1/2. What's S naught prime? S naught prime from here, S naught prime is plus or minus the square root of q. And what would S naught prime prime be? It would be q prime over 2, again, times the square root of q. So let's erase this. So S1 prime is equal to minus 1/4 q prime over q. Okay? And so S1 is equal to minus 1/4 log of q. You've seen all this before. We've done this in class. Okay? So if I stopped over here, I would conclude that y is asymptotic to e to the 1 over epsilon times plus or minus the integral of the square root of q. And the exponential of minus 1/4 log of q would be q to the 1/4. So this would be if you just throw away S2, S3, S4, just throw all that stuff away, that's the conclusion. This is called the WKB approximation. And this is what we have seen in class. Okay? What could possibly go wrong? It's very interesting. Basically, nothing can go wrong unless q is equal to 0. Because if q happens to be 0, then y is infinity. Ah! That can't be right.
But if q equals 0, we can't calculate S1. This is what I was saying.
You said S1 equals 0.
I said if S0 equals 1, if q equals
If
0,
S0 equals...
if q equals 0, we can't calculate S1.
Oh, you said that. Oh, I thought what I thought you said was if S1 equals 0. Okay, but you said, okay, good. So this could be a disaster. What does it mean physically if q equals 0? What happens at the place where q equals 0? Well, you go all the way back up at the top of the board. And remember, q is v of x minus e. What happens if q equals 0?
The turning point of the...
That's called the turning point. Okay? The particle, that happens when the total energy of a particle is equal to its potential energy. If the total energy of a particle is equal to its potential energy, then the particle has no kinetic energy. So the particle has stopped. So if the particle stops, all hell breaks loose. It's a disaster. Okay? And what I'm going to explain to you to do, this is the incredible calculation that you do with WKB, is how to handle this problem. This is the deep, difficult problem with WKB. It's going to take me a whole lecture to explain to you what to do when q is equal to 0. And when we solve this problem, we will understand at a very deep level the nature of quantization. Okay, that's where quantization comes from. Okay, any question? Yeah. Question.
My question was a little bit further back about the phi to the 4.
Yeah.
So we basically understood how the series for phi to the 4 theory diverges from this quantum mechanical model. Could we also come up with a quantum mechanical model which would tell us how the asymptotic series for QED or QCD would converge? Or
Tibor, if you have ideas on this, we're going to write a prize-winning paper. Okay, let me tell you, people can understand the divergence of what is called super-renormalizable theories. So that means phi to the 4 theory in less than 4 dimensions, 4 minus epsilon dimensions. Okay? Then we can understand that the perturbation series really diverges like n factorial. As you reach 4 dimensions, which is the critical dimension for phi to the 4 theory, the graphs themselves can become very big for the
Right.
first time. Now, and this is what happens in any theory when you reach its conformal limit, okay, when it becomes renormalizable instead of super-renormalizable. This is an unsolved problem, okay? And the one place to begin is also to understand what's going on in electrodynamics. What happens with electrodynamics? And nobody knows. This is a fantastically interesting problem. I regard it as really gripping. The consequences are immense to understand what is going on. But it means basically that you have this dispersion relation that I proved to you. The significance of that is we have to understand what happens in electrodynamics when you reverse the sign of alpha. Okay? If you reverse the sign of alpha, then the Coulomb force changes, and particles of like charges are now not repelling, they attract. And particles of unlike charges, a plus charge and a minus sign, repel each other. Okay? So why is the vacuum unstable? It's unstable because, you know, if this is a vacuum, in electrodynamics, you have virtual pair production, plus and minus. In conventional electrodynamics, they attract each other and disappear back into the vacuum. But if we have to change the sign of the coupling constant, in this case the coupling constant is not E, but alpha. Okay? So if alpha, which is E squared, alpha goes to minus alpha. So E is replaced by I times E. Okay? Now the vacuum is unstable. Okay? If the vacuum is, how do you understand the vacuum being unstable? When you create a virtual plus and minus pair in the vacuum, they now feel a repulsive force, so they push each other away. Now, do they push each other away to the end of the universe? No, because they only last a very short amount of time. The amount of time they last is given by the uncertainty principle, delta E. Delta T, delta E is about h bar. So delta T is very short. So they only last a very short time and then they disappear back into the vacuum. So you might think the vacuum is stable. But every once in a while, very, very rarely, this is so large, okay, there's a distribution of delta T's, that the particles have a long enough time to push each other far enough apart to gain enough energy to pay back the energy they borrowed from the vacuum in order to come into existence in the first place as virtual particles. And they are now real particles, and they're traveling out to infinity. That's what tunneling is, okay? They've tunneled through the barrier. They've gone far enough that they can roll down the other side of the barrier, okay? So very, very, very slowly, particles tunnel off to infinity. You have a huge pile of positive charges over here, all stuck together, and a huge pile of negative charges over there, all stuck together. Okay? This is a very slow process. The vacuum lasts a very long time because it's only very rare that a particle can last long enough to tunnel out to infinity. Most of the time when a particle tries to tunnel, it just comes right back again. It doesn't succeed. Okay? The vacuum becomes unstable, slightly unstable. This process is Hawking radiation. Okay? It's tunnel. Particle pair being created, and the particle tunnels out to infinity. Hawking, it's basically Hawking radiation. It's precisely the same idea. Okay? And so the vacuum is now unstable, and we have to calculate the lifetime of that vacuum state, and then take its nth inverse moment. And that tells us whether or not in electrodynamics, tells us how rapidly the perturbation series diverges. Some people think that the perturbation series does not diverge like n to the n, as in boson theories, but log n to the n, or something like that. Or possibly, so there are various conjectures about how it might behave. Nobody knows. This is an unsolved problem. Boy, would I love to know the answer and how to crack into that problem. Maybe you can get it by studying Feynman diagrams in electrodynamics having arbitrarily large number of vertices and study the asymptotic properties of those stuff. Really, really an interesting problem. I mean, there's a lifetime of research in that area. So I've written lots of papers on this, but this is just, the big problem lies ahead. This is where there's a whole huge area of potential research papers.